Dear student, warm welcome to NPTEL Phase 2 program video course on Geosynthetics Engineering in theory and practice. My name is Professor J.N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. This lecture number 39. This module 7, lecture 39, Geosynthetics for steep slope. I will now address the recap of the previous lecture. I have gone through the Joyle's method for slope stability analysis. I have covered the design example and software for steep soil slope. So, you now know that what is the different types of the methods we have used for the design of reinforced steep soil slope, and we have used the Scammern's method where you can change the length of the reinforcement at the bottom as well as at the top. But in case of Joyle's method, you have considered the different pore pressure ratio, and based on the pore pressure ratio, we have calculated that what will be the K required based on the slope of the embankment and also the angle of friction of the soil. And also we have calculated that what will be the L by H ratio due to the sliding and also L by H ratio due to the overturning, and then based on that we have selected that what will be the length of the geogrid and what should be the spacing. Now I will focus on the back wrapping technique for reinforced soil slope. So this kind of the technique is particularly suitable for the slope where space is restrained. You cannot place the reinforcement up to a certain length. For an example, I want to construct a steep slope. So this is the slope which angle is equal to beta, and you can see that sometimes you cannot go beyond this length. Suppose if the length is required more, so you can place a one layer of the geogrid material here, and there is no space. You cannot use this space, like let us say any concrete railway or is a steep slope, and you cannot go beyond this line. But as per your design, you require the length of the geogrid from here to here. So if the length of the geogrid is here to here, so if we want to place the reinforcement up to this length, so it is required to excavate this portion of the soil, entire portion of the soil you are to be this portion of the soil are to be excavate, and then you can place this length of the geogrid up to this portion. Now, instead of this, you are not required to excavate this portion. You can provide a back wrapping. You can back it, the reinforcement, like this. And you can also facing element, you can back wrap like this. So, this is what is back wrapping. Instead of this length, you can back wrap this geogrid material like this. So, there will be a development of the passive resistance here. Like this, you can place the another geogrid material like this. You are giving the back wrapping technique. So, this is what we call the back wrap technique for reinforced soil slope. So, you can save the cost, you can save the geogrid, and it will give very good passive resistance. So, you can reduce the length of the geogrid. So, this is what we call the back wrapping technique. Apart from that, instead of the geogrid, also you can place the geocell as a layer of reinforcement material. So, it will give the geocell material is a very good confinement effect. So, that way also the length of the geogrid can be reduced. So, this back wrapping technique has been used, and some design chart has also been made, and also we have adopted that two-way systems here. You know that what is two-way systems, the dual method is based on the two-way system, and this is the figure, the back wrap technique for reinforced soil slope, you can see here, and this is the geometry of the bilinear reinforced soil slope. So, you know what is this height of the reinforced slope, this is the length of the reinforcement, and this is the two-way system, and from this, that Sindhan Mandal 1993, that various design chart for slope reinforced with geogrid using back wrapping technique has been developed under different pore water pressure. When the pore water pressure RU is equal to 0, so from this chart, this is the slope angle beta, this is the pi angle of friction, and this is RU, that is gamma by delta H is equal to 0, and this is the geogrid force coefficient. So, this is K. So, knowing the value of the beta and the soil friction angle pi, so you can calculate the geogrid force coefficient, that is K required. So, you will be knowing K required. So, you can be knowing what will be the T related with the K, and can determine the what will be the strength of the geogrid material. From the right side also, this is the correlation between the slope angle and the geogrid length to slope length, that is L by H. So, knowing the angle of the beta and the soil friction angle, so then you can calculate what will be the L by H. So, that ratio you can determine. So, if you know that what will be the height of the reinforcement, so you know the what, then you can calculate what will be the length of the geogrid. So, you know the length of the geogrid, you assume some value of the spacing between the two geogrid material, and then you can design this back wrapping technique system using this chart. So, this is one chart when pore water pressure RU is equal to the 0. Similarly, when the pore pressure ratio change RU is 0.25, this also curve relation between the slope angle and geogrid force coefficient, and this also slope angle with the geogrid length the to height ratio. Similarly, for the pore pressure ratio RU is 0.5. So, from left side curve you can chart, you can determine what is geogrid force coefficient K required, and the right side you can determine what is L by H. So, I have already solved this related kind of the problem earlier by the Joel's method. So, here I am just presenting these three charts for the bag wrapping technique with the three different pore pressure ratio which you can use. Next, I will talk about textile technique. This after Lepala by 1982. So, this is a machine was specially designed to deliver 23 meter cube of granular soil mixed with polyester fiber in 1 hour. So, and this continuous polyester thread were coming out through the granular soil from 40 number of bobbins at a weight of percentage of 0.1 to 0.2 percentage. So, this is the kind of the system, this is the drum, and the soil is inserted into this drum, and this is the bobbins. This is a machine, this, and from this continuous polyester in the form of thread, and that is 0.1 to 0.2 percentage is out, and then mix up with the soil. This is a kind of the thread. It is very popular in France, and I have seen this kind of the machine also in the France, and then how they have been used in for slope stabilization in their country. And then you have to spread near to the slope. So, it is a mixture of the soil and the thread, and then you have placed any kind of the slope, and after sometimes this there will be a green grass will grow and it looks very greenery. It has been used exclusively in the France, and you can see bobbins at a weight of percentage only 0.1 to 2 percentage. So, what is the most important here is that it has been observed that apparent cohesion value of the fiber mixed soil was more than 100 kilopascal. After Lepala and Loiseau 1986, the technique can be used to stabilize the embankment and steep slope. The system has been successfully used in France to stabilize the steep highway slope of 60 degree, and it has been found that it is stable. The textile technique has quite been interesting and widely used for widening for the railway and the highway embankment. Only by find that this is a kind of the huge equipment where you require for proper kind of the mixing, because this fiber should be mixed with the soil and there will be no segregation, and then you are directly place the mixture of the fiber and the soil along the slope, and then you can find that grass can grow and it looks very greenery, and it has been mentioned that it is also the steep highway but in slope of 60 degree, and it is very useful So, this is a one kind of the textile which is developed by Lefebvre, and also that if you wanted to widen of the highway or railway embankment by applying the same technique, that is textile technique. Suppose this is the embankment, highway or the railway, and you wanted to extend this portion. We have observed that you can use the number of the layer of the geogrid material. You can also use that kind of the geocell material. Also you can use that geofoam material. Apart from that, you can use this kind of the fiber soil mixture, and you can place it and you can widening the road. It is also very stable. We have been perform many laboratory tests using the different percentage of the fiber element, and we found also it is very encouraging result, and we have also used in a centrifuge modeling. I will show you later that how this system also has been used in the centrifuge modeling and what kind of the failure may occurs and how it is stable. And also we have compared the both with the fiber mixed soil as well as the geogrid as a reinforcement. So this is very interesting. We can have more information later on in my next lecture. Now I will talk about the design of 300 meter. It is about 305 meter high artificial mountain using geosynthetics. This is Lauti and Mandal and 2012. This is the project. It has come from some Middle East country to our department to design a 300 meter high artificial mountain, and the king wants that it should be made of only sand, but it came to structural my colleague, and they started working with the steel as a material, and it found that it will be very expensive, but the client wants that it should be locally available material, and that is the sand, because huge quantity of sand will be available, and as you know that he wants that it will be artificial. So two of my students have worked out and designed this 300 meter high artificial mountain using geosynthetics. You can also have details of this paper which has published in ASC. So here available flat area at top about 3600 meter square, and as I said that sand was used as the main construction material. And you can see this is a circular cone frustum shape soil embankment reinforced with the geogrid, and it is there is a three road. So one from the bottom with the car, and it will go like this and on the top. So you can have a very magnificent view at the top, and this about 70 meter, the top diameter about 70 meter and bottom diameter about the 600 meter and height is about 305. There are 3 roads. The vehicle can pass, go up and one vehicle can go down. If there is any accident, that is why it has been provided with the another road. So 3 road also has been designed. So here I will just focus how it has been designed. What is the design approach for this? So this is molded as a 2-dimensional magnet in RESA 30, that software which is developed by Lec-39 in 2001, and facing angle of 50 degree to be achieved for practical purpose. Now there is a limitation of the software. So model is scaled down with a factor of 3. So geometric property decreases and unit of the soil increases by 3. This is what we call the method of scaling. Without the method of scaling, then this software will not accept. So that is why we have to bound to scale down this method. So unreinforced structure analyze for first hand idea of reinforcement. So initial guess of the reinforcement property by the method of the chart given by Joel 1990, which I have described the defined types of the Joel chart or method. The estimated reinforcement parameter like length, strength, etc. are reported along with the safety maps. This can aid in designing high rise soil structure reinforced with geogrid. Now what are the input parameter used in the software after applying the scale factor of 3? So you can see here soil property and soil type, it is in the written and the foundation, and internal friction angle pi, that is for written it is 35 degree, for foundation it is 40 degree. Coefficient C in kilopascal 0 for written and 0 for foundation, and unit weight kilonewton per meter cube for written soil 60 kilonewton per meter cube and foundation 20 kilonewton per meter cube. You can see how we have applied the scale factor to 3 times. That is why the unit weight of written soil is 60 kilonewton per meter cube. Now reinforcement stage, the 2 types of the reinforcement have been used, that is 3000 kilonewton per meter and 2100 kilonewton per meter. This is very high strength of the geogrid material. Most of the time that very high strength geogrid material have not been manufactured, but nowadays manufacturer has come up where it is required very high strength of the geogrid material. For example, where it is related with offshore, onshore kind of the project where you require very high strength geogrid material. So if it is required, manufacturer can also manufacturing the very high strength geogrid material. Now here that 2 types of the geogrid has been used. One geogrid name is geogrid U 3000, another geogrid U 2100, that is type 1 and 2, and ultimate tensile strength of the geogrid is 3000 kilonewton per meter and 2100 kilonewton per meter. So these are the reinforcement strength. Then interaction parameter. So as I say that geogrid name geogrid 3000 and geogrid 2100, and interaction parameter is from the direct sliding and the pull out. So direct sliding, what should be the CDS pi for GeoGrid U3000 is 0.8 and GeoGrid 2100 is 0.8, and for the direct sliding CDSC cohesion, that is 0 and 0. But for pull out CI for GeoGrid 3000 0.8, alpha value also 0.8, GeoGrid 2100 for CI is 0.8 and alpha is 0.8. You know what is the alpha, which I have already discussed earlier about the pull out test and how the alpha value can be used in case of the GeoGrid. So, alpha value for GeoGrid is considering 0.8. So, this is the reinforcement strength and the interaction parameter for direct sliding and the pull out. Now, what should be the input model in RESA software? So, this is the model. You can see this is the point number 2, this is point number 2, this is the x coordinate, this is y coordinate, and this is soil layer is the retain, and this is soil layer in the foundation. That means this point 2, this is point 2, and you are applying the scale factor 3. So, this is coordinate, x coordinate is minus 100, because base diameter is 200. If the scale factor is 3, basically it is the 600. By applying the scale factor, this base diameter will be 200 and the top diameter will be 24 meter and overall height will be the 100, because if you take with adopting the base factor 3. Otherwise, this will be the 300, this will be the 600 and this will be the 48. So, this is 2 point, x coordinate is minus 100 and y is 0. For the point number 3, that means this is point number 3, the x coordinate is minus 12, because this diameter is base top diameter is 24. So, this will be the 12. So, for the point 3, this is 12 and this y coordinate is 100, and for the 4, this will be the 12 and this will be the 100 for 4 point. For the point 5, that means this for the point 5, this will be the 100 and this 0. And for the foundation, you are taking this 1 and this 6. So, 1 is minus 1000 and this is 0 and 6 is plus 1000. So, this is the input model in the RESA. So, applying this scale factor 3. So, now you can see safety map for unreinforced structure. First of all, we have performed and find out that what should be the minimum factor of safety for unreinforced structure. So, here you can see that critical surface is the one, and you have to find out the critical surface for sliding a number of tall arc to be made for the different tall circle, and then ultimately you have to find out what should be the minimum factor of safety or what should be the critical slip circle, and then you can calculate that what will be the minimum factor of safety for unreinforced soil. Here you can see for the unreinforced soil the minimum factor of safety is 0.63. So, this is 0.63 because it is unstable then. So, it is not a stable structure. So, you require some reinforcement. Now, this critical shift circle and the wedge in the reinforced case. So, these are the reinforcement different layer and with the placing with the different strength have been used, and you have analyzed with the critical wedge as well as the critical shift circle. So, this is the critical shift circle and the wedge in reinforced case, and then you have to check what will be the factor of safety for this case. So, we are adopting the desired factor of safety, let us say 1.3. So, that is the desired factor of safety. Now, here it is shown safety map of reinforced structure. Now, we apply the reinforcement. This is by rotational analysis top. You can see that number of the shift circle, and here we have used the reinforcement, and then we find out that what should be the factor of safety. So, this is the check code for safety factor. You can see that here what is this failure occur or shape what it should be this zone. So, this is the rotational analysis tool. So, here the minimum factor of safety 1.30. So, it is the safe for rotational analysis. Now, what will be the translational analysis? This structure may collapse due to the translational. So, here the translational analysis bottom has been done, and you can see that what will be the failure here you can see. So, here the minimum factor of safety is 1.30. So, this is minimum factor of safety 1.30. So, it satisfies the both the criteria. Apart from this, it is also essential for the seismic analysis. As per ASTO 1993 guideline, a minimum factor of safety 1.1 is required for seismic analysis. A maximum horizontal ground acceleration of 2 meter per second square was used here during the analysis. We have the different zone, and from the different zone you will be knowing what will be the maximum horizontal ground acceleration of that zone, and it has also given in the different specification. So, here we have considered the maximum horizontal ground acceleration of 2 meter per second square for this analysis has been used, and we require desired factor of safety for seismic analysis is equal to 1.1. Now, we see that what is happening for the rotational analysis top, and here is the safety map for the reinforced structure due to seismic. You can see due to the seismic what is happening, and you check the code safety factor. This minimum factor of safety is 1.10. So, this is for the rotational analysis. And next, for the translational analysis. So, you can see for the translational analysis with seismic effect, and you can see that what kind of the translation of slip surface, and this is the color code for the safety factor, and this is minimum factor of safety is 1.08. So, we have checked in the slip, also we have checked with the translation analysis for both for the static case and as well as also seismic case, and we find that it satisfies that what will be the desired factor of safety. So, this way this design has been made. After optimizing the reinforcement parameter in RESA 53.0, the obtained value corresponding to the required factor of safety are scaled up for the actual structure. So, this is the final reinforcement length and the strength. So, elevation from the base in meter 0 to 30 meter, the length of the geogrid is 160 meter and the geogrid strength is 1000 kilonewton per meter. And we are considering the vertical spacing among the geogrid reinforcement means 1 meter. I am showing you this. This is the two-dimensional reinforcement layout for the real structure. So, here from the bottom, that what I say that 0 to 30 elevation meter. So, this is 0 to 30 and length of the geogrid is 160 meter and strength is 1000 kilonewton per meter. So, that is why from 0 to 30 the length of the geogrid 160 meter and geogrid strength 1000 kilonewton per meter. Now, 30 to 90. So, you can see from 30 to 90 here. So, here the length of the geogrid is 150 meter and strength of geogrid is 1000 kilonewton per meter. That is why 30 to 90, 150 length of the geogrid and geogrid strength 1000 kilonewton per meter. Now, again from 90 to 135, that means from 90 to 135, this zone where length of the geogrid is 135 meter, but ultimate tensile strength of the geogrid is 700 kilonewton per meter. So, here 135 length of the geogrid and geogrid strength 700 kilonewton per meter. Now, next 135 to 205 and length of the geogrid 120 and geogrid strength 700. You can see here the length of the geogrid is 120 meter and the ultimate strength is 700 kilonewton per meter. And next, that is 205 to 305. This is across the width and length of the geogrid is 700 kilonewton per meter. So, here from here to here across the grid, this is 700 kilonewton per meter. And spacing is keeping constant, the spacing is 1 meter. So, you can see very high strength of the geogrid at the base and the lower strength of the geogrid at the top, and this is about 300 to 300 means about 600 meter width, and this height of this structure about 305 meter, and this width is about 75 meter. So, this space has been kept that open, and sometimes there may be any copy or these shops, and then people can go on the top of this embankment and can see a sightseeing from this place. So, this is all the dimension are in meter. So, what is the summary or the conclusion? The study present the reinforcement parameter for a 300 meter high artificial sand mountain, and geogrids were used to maintain a phase angle higher than the sand internal angle of friction. Both rotational and translational analysis 2D have been performed for the structure using RESA 5 3.0. Strong 3-dimensional effect due to the geometry of the structure were expected to stabilize the structure by about 30%, resulting in an increased factor of safety. However, no strong conclusion can be done on 3D effect without detailed study. FHWA NH1 00043 guideline were followed during the manual calculation to obtain the initial input parameter for RESA 5 3.0, and heat and towel method was used to optimize the reinforcement parameter and achieve the desired factor of safety. The obtained reinforcement detail can be helpful in designing high-rise reinforced soil structure. So, we have the idea that how you can also design a very high reinforced soil slope. This some of the steep face slope with this mesh facing, and these you can see some also the green face also steep slope has been also constructed. Also some also is coming about the slope about 100 meter in India, and this is steep slope and soft face with the berm. This is what the geogrid reinforcement has been used, and this is the berm. Next I will that present our National Geotechnical Centrifuge facility in IIT Bombay, and it courtesy to my colleague Professor Viswanathan. And this is the National Geotechnical Centrifuge, and this is only the first of its kind in India. The technical detail of the large geotechnical centrifuge at IIT Bombay, the radius from the axis of the rotation to basket base is about 4.5 meter, acceleration range at 4.26 meter radius is from 10 G to 200 G, maximum payload at various G level. So, if the G level is 50, payload is 2500 kg, if G level is 100, the payload is 2500 kg, and if G level is 200, this payload is 625 kg. And rotational speed of the centrifuge R is 46 to 205 RPM. And configuration, this is the swing bucket at one end of the arm and adjustable counterweight at the other end, like this. This is counterweight and this is the bucket is here. So, it can be adjusted. So, this is the swing bucket at one end of the arm and adjustable counterweight at the other end. And soil model size. So, here you can make this model, I can place here and counterweight is here. So, this model size is 0.9 meter into 1 meter into 0.65 meter, or you can make 0.7 meter into 0.7 meter into 0.8 meter. So, basket base dimension that clear about 1000 millimeter into 1200 millimeter, and the run up time is 6 minutes to reach 200 G, and run down time is 6 minutes from 200 G to 0 G, and it will continuous run time for the 5 days. I must appreciate or acknowledge my past colleague Professor V.S. Chandrasekharan, who has taken this initiative and developed and the fabricated in situ in India, first of its kind in centrifuge modeling. I was associated initially as a member of this group. So, scaling law, this is quantity and prototype and model, because this centrifuge modeling is required what it is not possible to know that what will be the behavior of the soil. You know that when we are insulating the pile at a very deep depth, so it is very difficult, but using this centrifuge modeling you can scale down. For example, that if the length of the pile is the 20 meter, so you cannot that perform the test with the 20 meter length of the pile, but in a centrifuge you can model down by scaling. Let us say it is 8 centimeter. So, you can scale down and can perform that test and you can obtain the accurate result, and that is why it is required the scaling law. So, you can see from the scaling law what is prototype and what is model. So, length prototype in model 1, area prototype in square model 1, volume prototype in cube and model 1, velocity prototype 1 model 1, acceleration prototype 1 model in, mass prototype in square model 1, force prototype in square model 1, energy prototype into the power cube model 1, stress prototype 1 model 1, strain that is prototype 1 model 1, mass density prototype 1 model 1, energy density prototype 1 model 1, time dynamic prototype in and model 1, time diffusion that is prototype in square model 1, and time creep prototype 1 model 1, frequency prototype 1 and model n. So, these are the scaling law. So, if we use that, for example, very high strength of the geogrid material, and then accordingly you could to scale down that very thin geogrid material. So, here that some experiment also have been performed in 2002, where here you can see that the number of the layer of the reinforcement, here this black color you can see the number of the layer of the reinforcement, and the sand has been used as a filling material. So, then you have constructed slope like this. So, this is the model reinforced slope at 1G. This is the National Geotechnical Centrifuge Facility at IIT Bombay, and next the model reinforced slope at 30G. You can see when it is been 30G, then you can see what is happening in the model. You can see that naturally the kind of the slope failure may occur, but here it is not properly visible, but you can see later little bit more about this. Now, next when the model reinforced slope as 80G, you can see this soil is pushing towards this direction and there is a possibility of the ship failure of the reinforced soil slope like this, and this model reinforced slope at 80 G. Also, some of my students also have used this centrifuge modeling for, I was telling, the fiber and the geogrid fly ash slope. So, this is the basket for fly ash slope and also glass fiber as a reinforcement is used. This white color is the glass fiber, and this centrifuge test has been performed. This is small scale one centrifuge has been used, and you can see that typical failure, slope failure of the structure, where we have used the fly ash and also the glass fiber as a reinforcement. Also, that number of the layer of bamboo geogrid also has been used and performed the test with the centrifuge modeling. And here the finite element model using the geogrid reinforced soil slope has been also used. So, what are the major findings? Due to the fiber reinforcement, the settlement of the slope reduces and it fell at higher value of G. Finite element analysis on geogrid reinforced slope shows better performance than that of the fiber reinforced slope. However, there are several advantages of the fiber reinforcement. And now I have covered here that how that you have used this model, that bag wrapping technique, what the passive resistance also is developed, how it has been made, the design chart for the different pore pressure ratio, where RU is equal to 0 or 0.25 or 0.50, and from this design chart you can calculate that what will be the tensile strength of the geogrid material, and also you can calculate what will be the length of the geogrid. And next I have also discussed about the 305 meter height reinforced steep soil slope using the sand and geogrid as a construction material, and this material, this sand is easily available, and you can see that how we have used the RESA models software package has been used, and how this, for this model, how the scale has been down, and how the strength of the geogrid material has increased, and also unit weight also has been increased, and how the geogrid strength also has been decreased, and ultimately we have calculated what will be the factor of safety for the rotational failure as well as for the translational failure. It is under both for in the static condition as well as in the seismic condition. And you have seen that how this road also have been performed, but I have not gone to the details about the road and the foundation problem there. And at the end we talk about our centrifuge modeling, and the number of tests have also been performed. We have been used that geogrid material, even then geotextile material, even then fiber, defined types of the fiber material, and we find how it is more effective and stable that slope can be constructed. Apart from that, also we covered that textile method, how the filament or the thread mixed with the soil has been used for the slope stability. With this I just finish my lecture today. Please let us hear from you. Any question? Thanks for listening.